Good morning, candidates. My name is Abdurashid Makwata. Welcome to today's chemistry lesson. This online learning is brought to you in courtesy of IDET Girls Group. Today, we are going to look at reaction rates and reversible reactions. It is a third topic of Form 4. So let's look at what are the objectives of this topic. So this topic has two wide areas, that is the reaction rates and reversible reactions. On the reaction rates, we are going to look at the definition of reaction rate. What do we mean by reaction rate? Then we look at two theories that explains reaction rate, that is collision theory and activation theory. Then we shall look at the effects of concentration, pressure, temperature, surface area, and catalyst on the rate of reactions. So generally, we'll be looking at factors affecting the rate of reaction. We shall look at all the 5 factors that affect the rate of reactions. Then there is that part, the practical part, where we look at the experiments involving those reactions, the factors that affect reaction rates. So that's that practical on concentration, a practical on temperature, practical on a catalyst, and a practical on surface area. So that one we shall deal with it when we be looking at practicals. Then we shall then look at the reversible reaction, the second part of this topic, where we'll look at the equilibrium as a state of balance. We'll define equilibrium and some other terms. Then look at the effects of changing concentration, pressure, temperature on position of equilibrium. So shall look at what are the factors affecting equilibrium, how pressure affects equilibrium, how temperature affects equilibrium, and how concentration affects equilibrium. Then we shall look at the uses of some industrial processes, that the conduct, the harbor, and some other processes. What are their uses? So on the introduction part, the reaction rates and reversible reactions, we start by defining what reaction is. So what is rate of reaction? So you have heard of the word rate. What does rate mean? The rate of reaction. So when we say the rate of reaction, we mean we define the rate of reaction as a measure of how fast reactants are converted into products. How fast these reactants are converted into products. We learned in Form 2 what a chemical reaction is. So a chemical reaction involves converting reactants into products. So when look at how fast these reactants can be converted into products, we call it the rate of reaction. We can also define the rate of reaction as a chemical reaction, or the time taken for a given amount of products to be formed. Or the other person can define the rate of reaction as the time taken for a given mass or amount of reactant to be consumed. So we know in a chemical reaction, the reactants are being consumed and the products are being formed. For you to say there's a reaction taking place, reactants should be consumed, then products should be formed. Then the reaction would occur. So there are different types of reactions. There's some reactions that are too slow. There's some reactions that are very fast, and there are some reactions that are very explosive. So, students, do you know some of the examples of reactions that takes place? So some of these examples of reactions are rusting. Rusting is a chemical reaction, but it's very slow. So we have seen this rusting in several situations, like the the iron sheets. When these iron sheets are used to build a house and are not maybe they are not painted, you can see after some years the color of the iron sheet changes. It changes from gray to some brown color. So the brown color is the coating of rust. So we say this an iron sheet has rusted. So the reaction has taken place. It is the iron sheet which have absorbed the oxygen in air to form iron 2 oxide. So the brown coating you always see on iron sheet is what you call the iron 2, the iron 3 oxide. So we say the reaction that has taken place is iron plus oxygen to form iron 3 oxide, and it's always hydrated iron 3 oxide. So we say that the reaction, the rusting has taken place. That's the chemical reactions. So you can say examples of rusting are very slow chemical reactions. And another example for slow reaction is decomposition of hydrogen during weathering. So we have seen that. Then some other reactions are too fast. Examples are neutralization reaction. An example is a reaction between an acid and a base. The two, most of them are explosive, but if you use a mineral acid like hydrochloric acid, maybe with a certain base, so in a few seconds the reaction will have been over. So examples of reactions that occurs too fast are the neutralization of an acid and a base, alkalis, to form an alkali solution. Then there's some other chemical reactions that you cannot experiment. They are very explosive. So examples are the reactions between potassium and water, and also the reaction between sodium and water, or sodium with some dilute acid, especially concentrated sulfuric 6 acid. They are very explosive. So they cannot be experimented in a normal laboratory. Then let's look at theories of rates of reaction. Theories of rates of reaction. And on this, there are two theories that explain the rate of reaction. The first one is the first one is what you call the activation theory. The activation theory, or the activation energy theory, and then the collision theory. So before we look at that, let's look at how they explain the rate of reaction. So in other terms, somebody may define the rate of reaction as a chemical as a change of concentration, or a change in the amount of reactants in unit time. So the change of concentration in unit time can also is called the rate of reaction. So we say the rate of reaction is equal to change in concentration of the amount of reactants over time taken in change of time. Time taken for the change to occur. So we look at the change in concentration divided by the time taken for the change to occur. So if you are told to calculate the rate of reaction, we take the change in concentration over, that is, change in concentration is equals to final concentration minus initial concentration, then divide by the time taken for the change to occur. That is the final time minus the initial time. Final time minus initial time. We can as well use the reactant to calculate the rate of reaction by by using the change in concentration in the amount of products formed over the time taken for the products to be. I mean the change in concentration for the amount of reactants over the time taken for the change for the time taken for this change to occur. So you can either use products or reactants. Let's look at this. Let's look at these theories. The collision theory. The collision theory is an applicable for kinetic theory of matter, which assumes that matter is made up of small, tiny particles, in which like ions, atoms, and molecules. The collision theory has some proposals. So I'm saying that this collision theory is an application of kinetic theory of matter, the one you are taught in Form 1, the kinetic theory of matter. Can you still state the kinetic theory of matter, students? So state the kinetic theory of matter. Okay, good. So the kinetic theory of matter states that matter is made up of tiny particles which are in continuous random motion. Or we define a chemical, kinetic theory of matter. So we know matter is just anything that occupies space. So it can be a solid, a gas, or a liquid. So according to the kinetic theory of matter, this matter is made up of some tiny particles. It's made up of very tiny particles, and these tiny particles are in continuous random motion. They are moving. These particles are moving from one point to another. No, not necessarily from one point from another, but they are vibrating. So there are some occasions, like in solid, where these particles vibrate in fixed positions. So if the particles in matter vibrate in fixed position, we call that matter a solid. So they don't move from one point to another. That is now a solid. But there's a point where these particles move from one point to another, but within this matter. They move from one point to another. They vibrate as they move from one point to another, but within this matter. We call it now, if they move from one point to another, but it's just within the matter itself, we call it what? A liquid now. So particles in a liquid move from one point to another, but within the liquid. But there are some occasions where these particles move from one point to another. They move freely from one point to another. So they can move even very far apart. So we call it now a gas. If they're moving freely, they can exchange positions. We call it now that's in a gaseous state. So this is where this collision theory bases, and it proposes some rules that the reaction for the reaction to occur, reacting particles must collide. So according to collision theory, for reaction to take place, the particles involved should collide. So one particle collides with one another. Then two, not all collisions between reacting particles are successful in a reaction. So collisions occur, yes, but not all of them are successful in a collision. So what are successful? We say that collisions that initiate a chemical reactions are called successful collisions. Or we can call it fruitful collisions or effective collisions. So we are saying that not all the collisions are successful collisions, and for it to be called successful collisions, they should collision. There are those. The successful collisions are collisions that initiate a chemical reaction. So particles are moving from point to another. So when they collide, if they collide, then a chemical reaction takes place. We call that collision a successful collision or a fruitful collision. Then there is three. They talk of the speed at which particles collide is called collision or frequency. I mean collision frequency. The speed at which these particles collide is called collision frequency. And the higher the collision frequency, the higher the chances of successful collisions to form products. So we say that these collisions occur at different speed. So we say that the speed at which these collisions occur is what we call collision frequency. So if the speed is high, then the reactions will be very fast. If the speed is low, the reaction will be slow. Then the higher the chances of successful collision, the faster the reaction. So if there's a high chance of having so many successful collisions, then the reaction rate will be very fast. Then the average distance between solid particles from one another is too big for them to meet and collide successfully. So you can see in a solid, we say that these particles, these tiny particles that form a solid, they are vibrating, they are moving, but they are moving within fixed positions. They are vibrating within fixed positions. So according to collision theory, the distance between these particles that are moving, they are too far. The distance between them is too big for them to meet and collide successfully. That's why a solid cannot react. Just one solid cannot react on its own. So it has to be mixed with something else, or a catalyst or something else. So the distance between them is too far for them to meet and collide. So when somebody dissolving these substances in a solvent, make the solvent a medium for the reaction to take place. So if we dissolve the solid in a solvent, the solvent acts as a medium. Now the particles of the solid, they move from one point to another within that liquid. So in the process of movement, they collide. Then the reaction takes place. The solid particle distance is the solid particle distance reduces as the particle ions are free to move in the solvent medium. Then the successful collisions takes place if the particle colliding have a required energy and the right orientation, which increases the vibration and the intensity of successful or fruitful effective collisions to form products. So we are saying that for successful collisions to take place, one, it should have a required energy. Should have the required energy for it to do what? To collide with one another. Then you should have also the right orientation. To have the right orientation. So the two increases the vibration and the intensity of the successful or the fruitful or the effective collisions to form the products. So that's according to collision theory. What about the activation theory? The activation theory, or also called, it's also called the enthalpy of activation, the activation energy or the enthalpy of activation. So we define the activation energy as the minimum amount of energy which the reactant must overcome before they react. So there is some energy that reactants must overcome for them to react. So this amount of energy that the reactants must overcome before they react is what you call the activation energy. So what is this activation energy used for? This activation energy is normally used to break to break the bond used for breaking of reacting particles. So we know in a chemical, any chemical equation or any chemical products or the reactants, they have bonds. They are held together. The particles in a chemical compound or in a chemical compound, they have bonds. So they are attached together with the bonds. For the reaction to occur, these bonds have to be broken. So it is the activation energy that breaks the bond. So before the reaction takes place, the reactants have to overcome this activation energy. So the energy that breaks these bonds. So meaning the bonds have to be broken for the reaction to take place. So that energy, that minimum energy which the reactants must overcome before the reaction to call the minimum energy, the one that is used to break the bond. So the higher the bond energy, the slower the reaction of the lower the reaction, the start of activation energy. Okay, so the activation energy does not influence whether the reaction is exothermic or endothermic. So there's a diagram, an energy level diagram below here that shows the activation energy for exothermic and endothermic processes. So you can see what the activation energy energy level diagram. So there's a product A and B. A attached to A, B attached to B. Then if this activation energy is applied, then A has broken, the bond between A and A has broken, so it is just A and A. Then the energy between B and B has been broken, so it's just B, there are just two B's. Then after that, A reacts with B and another A reacts with B. So the process has taken place. So without this energy, the reaction cannot take place. So there must be this activation energy to break the bond so that reaction takes place. So next thing we are going to look at at measuring the rate of chemical reaction, how the chemical reaction can be measured. That's our next session. Bye.